Hello everybody, welcome to our second dynamics video. Today we are looking at drawing free body diagrams as well as looking at Newton's second law, and then we will jump into force of gravity as well, which is totally awesome. So free body diagrams are the diagrams that we are going to be drawing throughout this entire unit. Free body diagrams will help you solve these problems and kind of figure out what's going on with the problems. So a common free body diagram. So it doesn't matter if you have a car, a person, a toboggan, a spaceship, anything like that. We tend to draw them as a square. And we tend to imagine them as a point mass, or everything kind of comes from the middle. And then what we do is we draw all the forces acting on this body. So some common forces that we will see are force of gravity, we will see maybe applied force sometimes if you're pushing a block. Applied force, so force of gravity is F of G, applied force is F of A, or F of A PP they usually use, or FA works as well. And then force of friction we're going to talk about. So that is, should probably be using capital letters here. Bad habits. Bad habits. Force of friction, F of small f. So we're using those subscripts to denote what type of force we're dealing with. We talked a little bit about the normal force in the last video, normal force. And hopefully, once we talked about it in class, it made sense. We do Fn for that, which is going to be different than net force, which we'll talk about later in this video. You might see tension, which sometimes we denote as T, or force elastic, Fe. Elastic force, it is, yes, tension is definitely not. Sorry, I was thinking of Hooke's law. We want that to be here. Got ahead of myself. There we go. And then we'll never deal with air resistance, but if you wanted to, that's another one you could do. Air resistance, F, air. So what we do is we draw these forces onto this free body diagram in the direction that they're acting. So we know, for example, we don't really have a situation. There's no context here. Let me move that up a little bit. There's no context here, but we know gravity always acts downwards. So you could say, here is the force of gravity. And you know, for example, let's say it's this mass is sitting on a table. So we are going to have a normal force acting on that. And maybe maybe you are sliding along the surface. So there's an applied force here. You're pushing or pulling this, and friction is opposing your motion. Friction's going the other way. So something like that. That is a typical free body diagram. So that it shows all the forces acting on this object, and you can start to see what's actually happening. So you see here a toboggan is sliding across a horizontal surface with a constant velocity. I think it makes more sense to say is being pulled. Is being pulled across a horizontal surface with a constant velocity. So we're going to talk about why that constant velocity is important, but for now let's just draw our free body diagram. So I would say draw a free body diagram. So this is our toboggan. Again, everything can be drawn as a square, and then we put our point in the middle. So we know that the toboggan is being pulled across a horizontal surface. There's going to be a force of gravity on this and a normal force acting between the surfaces. The toboggan is being pulled, so I'm assuming it's being pulled by a rope. So that means there's going to be tension from the rope. And then there will be a little bit of friction, even though there won't be a ton because it's on snow. So for those of you who don't know what a toboggan is, it's a sled. It's a type of sled. Kind of looks like, let's see if I can draw it. Something like that. And then you sit. Yay. And then you go sledding or tobogganing. I don't know why they're tobogganing uphill. That's weird. Cool. So that would be a typical free body diagram. There might not always be this many forces acting on this. Like, for example, if we had a rock is falling off a cliff, draw the free body diagram. Okay, so we have this rock. That's terrible. Hang on. I'm trying to go too fast. We have this rock. It's falling off the cliff. So we know it's got a force of gravity on it. And if a rock is falling off a cliff, it will have a small bit of air resistance trying to slow it down. But other than that, that's the only thing. Yeah, only two forces acting on that rock. So it's not always going to have four. It might have two or one or three or whatever. But we will use free body diagrams for mostly every problem in this unit, and they will help. Let's move on to Newton's second law, so the second part of this video. So Newton's second law, you can think of it as an unbalanced force results in an acceleration. So we're starting to get into some math here. We've got a formula and we will use it. So an unbalanced force results in an acceleration. Newton's second law is defined with the equation F net is equal to ma, or F is equal to ma, as you will see. Something I didn't talk about in the video, but I will talk about in class is force is a vector quantity, but so it needs a direction, but we will have covered that in class. So F net is the net force acting on the object. Net force is also total force. M is mass. So F net is also in newtons, by the way. Newtons. M is mass, and that'll be in kilograms. And A is acceleration, and that is in meters per second squared. That is that is Newton's second law, and we will be using this throughout the entire unit because we will be looking at net forces always. And I think that one's on your formula sheet as well. And you can see this is exactly why forces are calculated in newtons, because if we say, okay, well, F net is mass times acceleration, mass is kilograms, accelerations is meters per second squared, and then kilograms times meters per second squared, and that's what we talked about in the first video. That just being a lot to write, so someone took that and said, okay, let's make that equal to a newton. So forces are always measured in newtons, but a newton really is, if you unpack it, a kilogram times meters per second squared. Let's dive in and use this formula. A 650 kilogram car accelerates at 4 meters per second squared south. What is the net force acting on it? Okay, well, we know mass is 650 kilograms. We know acceleration is 4 meters per second squared, and we are trying to find F net. So F net is equal to ma, and we know that we don't have to do any formula manipulation, which is great. So, nor do we have to do any unit conversions. 650 kilograms multiplied by 4.0 meters per second squared. And we get, it looks like we are going to get 2,600 newtons, or 2,600 newtons. The car is accelerating south. Therefore, our net force is acting in a southern direction. Hopefully that made sense. Okay, let's do another one. The Batmobile exerts a force of 8,500 newtons east, while friction pulls back on it with a force of 1,500 newtons. If it has a mass of 1,250 kilograms, what is its acceleration? So let's draw our free body diagram. That's my Batmobile. I know it looks a lot like my toboggan, but that's okay. So what forces are acting on the Batmobile? Well, it's exerting an applied force to keep it moving. And friction is pulling back on it. So friction is opposing its motion. Friction always opposes the motion. So friction is going the opposite direction. And then we have force of gravity. And it's on the road. It's on the road, so it's going to have a normal force. It has to have a normal force. If it just had a force of gravity, that means its motion would be going downwards. And we know that it's not just going to fall through the road. So in this case, we assume that force of gravity and normal force are equal magnitude, so therefore they're going to cancel each other out. We know this because the Batmobile is moving in a horizontal direction, right? So there's no movement vertically, which means there's no net force vertically. That means force of gravity and normal force are the same amount. We can just ignore them for right now. But what we want to do is look at, we know force applied is 8,500 newtons. We know force of friction is, so you got to be careful here. Force of friction is 1,500 newtons, but it's going in the opposite direction. So if we make this positive, this direction has to be negative, which means our force of friction is going to be negative 1,500. And we know mass is going to be 1,250 kilograms. So what we can do here is say, okay, well, F net is equal to MA. So net, this is total forces, right? F net. So you can actually split this into, well, what forces are we dealing with here? Well, we're just looking at the applied force and the force of friction. So in this case, we can just add those together because that's our net force. So that's the total forces. Total forces are going to equal to applied force plus force of friction, and that will still all equal to mass times acceleration. We want to solve for acceleration, so what we need to do is divide by m on both sides. It cancels out on this side, so now we have acceleration is equal to applied force minus force of friction all over mass. And we can start plugging things in. Applied force is 8,500 newtons. Force of friction is negative 1,500 newtons. So we're adding that negative force. Whenever you're looking at net force, you're adding all the forces together, and then you have to take into account their direction. And the mass is 1,250 kilograms. We can start to do some math here. That means we're going to get 7,000 newtons over 1,250 kilograms. And if we divide that out, we will get 5.6 meters per second squared. Obviously, if we have a larger force applied than we do a force of friction, then the Batmobile will be moving in that direction, which is the positive direction. So you could say positive, you could say positive 5.6, or you know that it was also in the east direction, which we did here. This is east, and this was west. So you could say acceleration is 5.6 meters east. So that's net force. We're going to use that throughout the entire unit. And I want to talk about one more thing before we go, and that's force of gravity. So force of gravity, this formula, well, the force of gravity formula that I'm going to introduce only works near Earth's surface, which, and by near that I mean like within probably 100 kilometers or so. It goes up quite a ways. The Earth is really, really massive, so it's huge. So the force is going to be very similar whether we're like at sea level or up on a mountain. So we know that F net. Let's do this. F net is equal to mass times acceleration. But near Earth's surface, everything accelerates at the same rate. Hopefully that makes sense. Everything and that acceleration, hang on, let's write that a little nicer. That acceleration is 9.81 meters per second squared. And we've learned that in our kinematics unit. That is actually a constant, which is really awesome. So, hang on, I just lost my notes here. I don't know where they went. We can probably just wing it, I think. Oh, here they are. Perfect. Okay, sorry. So that actually has become a constant. Acceleration due to gravity, we call it small g, which is 9.81 meters per second squared. So we can revamp this F is equal to ma into the force of gravity formula, which is F of g, force of gravity, is mass times gravity, right? Where gravity is the acceleration, the little g is acceleration due to gravity. So in this case, this is force of gravity. And that's in newtons, if my pen would work properly here. This is mass, and that's in kilograms. And this is acceleration due to gravity. It's a constant. It should be on your formula sheet, I believe, which it's always 9.81 meters per second, newtons per kilogram, same thing, meters per second squared. Hopefully that makes sense. And that brings us to mass versus weight. So mass versus weight. F of g is your force of gravity. It is also the weight of an object. And mass, m is mass. So there is a difference between mass and weight, because your mass is always going to be the same no matter where you are in the universe. You have the same mass, but depending on what planet you're on and what the acceleration due to the gravity of that planet is, your F of g can change, or your weight. So, for example, I think I am about 80 kilograms. That is my mass. I don't know if that's exact. I'm just kind of guessing. So that's my mass. But if someone ever asks you, how much do you weigh? Well, that's a bit of the wrong way to ask that, because in order for me to find out how much I weigh, I need to say, okay, well, I need to take that 80 and multiply it by 9.81. And I don't have my calculator handy. Here it is. 80 multiplied by 9.81 that puts my weight at 784.8 newtons. So now I can tell people when they say, well, how much do you weigh? I can say, well, I weigh 784.8 newtons or 785 newtons. So there is a difference between weight and mass. And you are going to see that those come up in the questions. So basically you weigh more here than you do on the moon because there's more gravity here than there is on the moon. So let's do a couple example questions. This is one of the longer videos. I apologize, but we'll get through it. This is our last example. How much does an elephant weigh on Earth if its mass is 4,500 kilograms? Well, that's the force of gravity is m times g. The mass is of the elephant is 4,500 kilograms, and g is always 9.81 meters per second squared. So in this case, how much does an elephant weigh? Well, we can calculate that by saying 4,500 kilograms multiplied by 9.81 meters per second squared. And we get an elephant weighs 44,145 newtons. There you go. So today, just as a recap, we looked at free body diagrams and drawing them. We looked at Newton's second law, F is equal to ma, or F net is equal to ma. And we looked at force of gravity. That's our first force that we looked at and that we're going to be using. Cool. Thanks for watching. Don't forget to like and subscribe.